Bob, would you introduce tonight's speaker for the Madison DX Club?
Right. Well, tonight we have Frank Donavan, W3LPL. Frank's been around a while. He got his license in 1959 when he was 12 years old. So he's been a ham for more than 60 years. And he's accomplished a lot in all that time. I think most of us probably know Frank and certainly recognize his call, W3LPL. He's a top-notch DXer and contester. And if you haven't seen his antenna farm, take a look on QRZ.com. And he has a nice Zoom tour of his antenna farm, which is quite impressive. He also is a professor at DX at the Contest University. He's also very supportive to amateur radio clubs, and one of his key things is that he promotes is the fact that how hams and clubs can help one another, and I really find that admirable. Anyway, Frank's an engineer, and I think probably a very technical guy by heart. His passions involve antennas and propagation. So this evening, Frank's going to tell us a little bit about how we can improve our chances in high HF DXing during this sunspot cycle. Frank, whenever you're ready, please go ahead.
Okay, let's see if I can do the screen sharing here. Very good. Well, thank you for that kind introduction. Like many hams, I was very fortunate in my career to kind of accidentally back into a career in which ham radio was of extraordinary value. I won't make a big deal out of it, but for quite a bit of my career, I wound up in the national security space business. And what that wound up doing was giving me an opportunity to work with experts in many, many areas, and one of those was physicists who with in-depth knowledge of space weather, because we were flying satellites in space, and it was pretty important to preserve these multi-billion-dollar investments. So having experts in space physics was a very important part of what we did. So I had a chance to interact with them. By no means am I an expert, but one thing I can do is to help relate some of this incredibly complex detail about space weather to hams, because I know the ham community very well, and it's fun to be able to share this kind of information with my fellow hams. So here we go. I published an article in May 2023 QST concerning the upcoming solar cycle 25. I think anyone who's active on HF has had a great time with solar cycle 25 so far. It really started in earnest at the end of 2022. Last year was great. This year has been wonderful. We've had just in the last few weeks, some really wonderful summer solstice solar maximum propagation that produces some really amazing nighttime openings all over the world. Until early this month, even 10 meters was open for much of the night. I'll talk a little bit later about why that's not true anymore, but it'll come back in the fall. So anybody who's interested in this topic can go back to May QST. By the way, I'll be publishing another article in October QST, which will mark about the middle of solar cycle 25. So when that gets published, there'll be about 2 years remaining. Somebody on here who's not muted.
And now.
Okay, these are 3 very excellent publications for those who would like to dive in deeper into the topic. The one on the right, Radio Wave Propagation, is very affordable, very easy to read, useful to have it on your bookshelf. The other 2 books are also very, very good. They were both extensively rewritten for the 100th anniversary of the ARRL handbook, and the antenna handbook was rewritten at the same time. The propagation chapter in the ARRL handbook is completely new. So for that chapter alone, it's worth the investment. The antenna handbook, the antenna book deals mostly with antennas and just touches on propagation. So you really need both of these books. For those who have some professional background or education in technical topics like physics or engineering or mathematics, this is also a very excellent reference. It's free. It's a little bit dated, but it's still a very excellent reference. There's a newer version of this that was published about 10 years ago, but it's extremely expensive. It's been out of print for a long time, and I'm lucky enough to have a copy of that one that I bought while it was still in publication, but it's out of publication and extremely costly now. But you can get the original one for free at the website address shown here. So let me say a little bit about my style of presentation. My slides have a great deal more detail than what I will address in my comments. You could always go back and look at the slides to get that detail. If the slides have been carefully prepared so that they're very readable, I don't feel any temptation to read these slides. I'll just focus on a few of the key points, and you folks can go back and look at the slide decks later if you want to dive in to the detail here. I'm also very careful in my choice of words throughout these slides, so that if you're interested in more detail, one thing you can do is to take the exact words that are in these slides and go to Google, and you can research those topics. All the wording I use is standardized wording in the ham radio community and in the professional community. So I think it's fair to say that all life on Earth originates on the sun. Without the sun, we wouldn't have life on Earth. And likewise, all HF propagation originates on the sun. The sun has an extremely powerful magnetic field, and it's what creates sunspots and the beneficial radiation from sunspots, and also some of the short-term problems that we experience, especially near solar maximum, things called coronal mass ejections. Anyone who was on the air on May 10th or 11th experienced some of the most severe propagation disturbances we've had in a long time. And we get quite a bit of solar flares, which I'll talk about later. They normally are relatively brief, usually a few minutes, sometimes as much as an hour. These are terms that every active ham should have some degree of familiarity with. Certainly everyone's heard about sunspots. Many of you have probably seen them, either online or seen them yourself with appropriate vision wear to protect your eyes. Certainly you can't look directly at the sun. The sunspots are contained within regions on the sun known as active regions. Not so far back, these were called sunspot groups or sunspot regions, but now they're referred to as active regions. They contain not only sunspots, but also solar flares originate from active regions, not very far from sunspots, and coronal mass ejections that caused the really severe propagation degradation on May 10th and 11th also originates from these active regions. So we're approaching the middle of solar cycle 25. The last solar cycle 24, which was a fairly weak cycle, lasted almost exactly 11 years. But solar cycles can be as short as about 9 years. It's relatively uncommon for them to be that short, or they can be as long as 14 years. We don't know what the length of this solar cycle is going to be, but it's probably going to be about 11 years. We'll see. The beneficial radiation from the sun that opens the 10-meter band at this part of the solar cycle, makes it into a really great DX band, opens 15 meters all night long, especially at this time of year. is a form of radiation from the sun known as extreme ultraviolet. Extreme refers to its wavelength. Fortunately for us who live on Earth, this extreme ultraviolet radiation is completely absorbed in the atmosphere before it ever gets to the surface of the Earth. If that were not the case, we wouldn't be able to live on the Earth. It's very powerful radiation. And this extreme ultraviolet radiation is what creates the F2 region, which is the primary area that reflects HF propagation for DXers especially. The other type of radiation that occurs from the sun is X-ray radiation from solar flares that can cause blackouts, but only on the daytime side of the Earth. I'll show a little bit about that a little bit later. And the geomagnetic disturbances, and that's what happened on May 10th and 11th, was a rather extreme case where coronal mass ejections was very strong, very powerful, and it turned out to be directed directly at the Earth. So we got the full effect of a coronal mass ejection. Most CMEs, as I'll refer to them, miss the Earth. The vast majority miss the Earth, and even those that affect the Earth are usually near misses. But when we get a direct hit, it can be pretty dramatic, as it was on May 10th and 11th. Especially if the orientation of Earth's magnetic field is opposite to the Earth. So we'll talk about that and the effect that that has, and that did occur for an extended period of time on May 10th and 11th. So the sun is a gas star, so it doesn't have anything like terra firma on the Earth. It's only gas. And because it's a gas star, its rotation period varies with latitude. And I'll show a schematic that shows the relative rotation period. For most of us, it appears to be a 27-day rotation, and that's because active regions on the sun, which contain sunspots, CMEs, and solar flares, they occur at the latitude where the sun rotates once every 27 days. The other thing that very, very strongly affects propagation is the Earth's tilted axis. The Earth is tilted 23.5 degrees. That's what causes the seasons on the Earth. And it also causes seasons of propagation. Propagation right now, and I'll just refer to it as the summer solstice season, is very, very different than it is during the winter. And the thing that's especially different about solar maximum propagation at this time of year is that many of the DX bands are open all night long. It's quite a treat during solar maximum, and we're having a lot of fun with that recently. So this it just captures some images of the sun from prior solar cycles. And what you can see during the course of a sunspot cycle is how the activity on the sun varies. If you look at the top part of the slide here, during solar minimum, you can see that things are relatively quiet on the sun. But when you get up near solar maximum, like we are now, there's a whole lot more activity on the sun, a lot more sunspot activity, a lot more coronal mass ejections, many more solar flares, and that's going to continue for a few more years. Commonly, in terms of describing the seasons of the sun as it goes through its 11-year nominal period, is as 4 phases. And right now we're in the solar maximum phase. That began at the end of 2022 and is likely to continue for roughly 2 more years. So that's where we are now. And then we will enter the declining phase as the sunspot cycle declines towards solar minimum. That typically lasts 3 or 4 years. And you can see from the images here that this activity on the sun declines. By about 2029, we won't be at solar minima, but there'll be so little activity from the sun that it'll seem like we're at solar minimum. And that solar minimum phase duration is quite variable. Sometimes it seems like it'll never stop. Like the last one, the last solar minimum lasted at least 4 years. During prior solar cycles, many of the solar minimums lasted more like 2 or 3 years. So let's hope the next one, if you're a 160-meter operator, you'll probably be cheering for very long solar minimums because 160 benefits from that. But if you really like the high bands, you might like to be done with solar minimum as soon as you can. So in my professional career, I have the opportunity to interact with physicists and scientists at the NASA Marshall Space Flight Center. And I have a lot of respect for the work they do. Above all else, they're responsible for the safety of human lives in space. And not only real-time forecasting of what's going on so that astronauts can protect themselves if need be from some extreme events, but also for forecasting in the longer term what various missions might experience, depending on when their mission is likely to take place. And of course, some of the most dangerous missions will be to Mars, where there's no magnetic field on Mars to protect astronauts, and there's going to be a lot of challenges with that. Well, Marshall Space Flight Center is the center of excellence for that kind of work, and I like the way they do forecasting. The URL at the bottom of this page shows where you can get monthly updates to this forecast. And they have an interesting way of doing this. So they've, instead of just producing a single forecast for solar cycle 25, the one we're in now, they produce 4 different versions of the forecast at various levels of likelihood. The one that's labeled 5th percentile is, I don't know why they publish this one still. It's very apparent now in the middle of 2024 that we're not on this fast track to a decline to solar minimum. So we can discount that red line. And if you look at the green line and the purple line, they've come pretty close together. A year ago, they were fairly far apart. But now the 50th percentile, which is kind of like coin flip, either it's right on or not, is the main difference between these two is that the green line suggests that solar maximum will start declining about 6 months sooner than the purple line. There's not a whole lot of difference in the amount of solar flux associated with those. If I were to look at these right now, my opinion is that we're more like on the purple line right now, but we could well be on the 50th percentile line, which is the 160 line. We'll know at the end of 2026 which one of those we're on. There'll be about a 20-point difference in solar flux at the end of 2026, depending on which of those. And then in the blue line, there's a very, very optimistic track. And I don't think we're on this track either. That suggests that the solar flux should be sitting around 180 to 185 right now, and that's mostly not happening. And occasionally it happens, but for the most part, it's not. So I don't think we're on that track, but it'd be great if we get on that track. So we'll be watching this over the upcoming 6 months to a year to see if we wind up on this 95th percentile track. So that's very optimistic, but it'd be great if that actually happens. So we've all heard about solar cycles. They normally last 11 years. what a lot of hams are not aware of is the sun actually has two solar cycles, a northern hemisphere of the sun solar cycle, and a southern hemisphere solar cycle. Now, normally they track pretty well. And if you look at solar cycle 23, the green line is the solar cycle in the southern hemisphere, the blue line is the solar cycle in the northern hemisphere, and the red line is both of those combined. So you can see that there was kind of a double humped peak back around the year 2000. But during the last solar cycle 24, it was a dramatic difference. Any of you who experienced solar cycle 24 in the year 2011, 2012, it looked like we had reached a very, very weak solar maximum, and then it started to decline fast. But then suddenly and unexpectedly, the southern hemisphere of the sun came to life, and solar cycle 24 was better than we expected. It wasn't as good as this one, nowhere as good as solar cycle 23, but still a lot better than we were expecting a couple of years before. So this slide shows a lot more detail, but the same concept. This is actual data taken from the website shown at the bottom of the page. And it shows the same data, but in much more detail, and it's much more current. So the blue line at the top shows the total sunspot number. It's the smooth sunspot number. And the main thing I want you to notice here is that now in 2024, the sunspot number is already significantly stronger than it ever was during the last cycle. And that's why 10 meters is so much better than it was 11 years ago. But the other interesting thing I'd like you to notice is the purple line. The purple line is the sunspot number for the southern hemisphere of the sun. And notice this anomaly. During the last solar cycle, the southern hemisphere of the sun was a lot more active than it is during this solar cycle. So the reason I want to point this out to you is just like during the last cycle, when we were so disappointed during the year 2012, and then suddenly the southern half of the sun really came to life during the year 2014, about 2 years later. The same thing could happen again, but I think it's relatively unlikely because and I'll show you in a bit, we're getting kind of late in the 11-year cycle, and if the southern hemisphere of the sun is going to come to life the way it did in 2014, it better get started pretty soon. So we've got some interesting things to watch for over the next year. This graph shows all of the modern sunspot cycles laid on top of each other, and they've all been calibrated in terms of when solar minimum began. So the month shown at the bottom where it shows 0, that was the solar minimum year for that solar cycle. The dotted lines is the current forecast for solar cycle 25. That's our current cycle. There's a couple of things I want you to notice about our current cycle. If you look at the really strong sunspot cycles, the ones that get up above 200, notice that they reached their peak earlier than we are in this solar cycle. They typically reach their solar maximum during the 4th year of the sunspot cycle. But we've gone past that now, and the further we go, the less likely it is that we'll ever get to one of these really high numbers. And the other thing I'll point out here is we're getting it to the point now in this solar cycle where it's inevitable that we're going to start declining. If you look at all of these solar cycles that are shown in all these different colors, you'll notice that by about 1 year from now, about the 5th year of the solar cycle, that all of those cycles start to decline. That's why I'm suggesting that if the southern hemisphere doesn't come to life pretty soon, that it's probably going to be too late. So, but let's hope it happens. This is another very important aspect of the solar cycle that most hams never hear about. The AP index is a measure of global geomagnetic activity, and geomagnetic activity is what causes degraded propagation. So during the more active years of the sunspot cycle, we get really good benefits of extreme ultraviolet radiation that open up the F2 region. But we also get things like cause the disturbances of May 10th and 11th. Well, you can clearly see on this slide that after we get beyond this point of the solar cycle, these disturbances become more common. And so we'll look, this is also from Marshall Space Flight Center. It's dated June 6th, so it's just a few days old. And you can see their forecast is for the 50th percentile, that's the most likely, that the disturbances that affect HF propagation will continue to become more severe over the next 3 years. And that's pretty typical of most solar cycles. So as the solar flux starts to drop, unfortunately, the A index will continue to increase for about 3 more years. And then it will also start its decline to solar minimum. And you can observe this monthly if you look at this website URL at the bottom of the page. Right around the first week or the 10th of the month, the Marshall Space Flight Center updates their forecast, not only of solar flux numbers, but also of geomagnetic activity. Okay, so let's take a look at some of these phenomena. In the upper left-hand corner is one of the largest sunspots that was ever seen, and compare that to the size of the Earth on the same scale. It's a truly massive sunspot. This was from about 20 years ago. So sunspots are what bring us extreme ultraviolet light and open the upper bands. Big sunspots like this is what tends to open the 6-meter band for F2 propagation, something that 6-meter enthusiasts were really hoping for, but it's been kind of disappointing so far. Solar flares also originate from the vicinity of sunspots, but they're not the same as sunspots. They're caused by magnetic activity. And this is an image, a photograph of a very large solar flare. Their effects on propagation are primarily relatively brief blackouts of HF propagation, but only on the sunlit side of the Earth. The primary thing that affects HF propagation from flares is X-ray radiation. X-rays travel at the speed of light. So it takes about 8 minutes from the time one of these flares explodes from the sun until it reaches the Earth and affects our propagation. Good news is they typically last, most commonly, for only a few minutes, occasionally for an hour or more. And usually the propagation returns to normal at the end of that period, just as if it had never happened. Another aspect that affects propagation much more frequently than the other problems is what are called coronal hole high-speed streams. Well, what does that mean? There are areas on the sun where the magnetic field of the sun extends far out into space, and that's illustrated in the cartoon on the left. Sunspots are labeled A on that cartoon, and they have closed magnetic fields that come back to the sun. But coronal holes are areas of magnetic activity where the magnetic field lines extend very, very far into space. And that allows plasma, magnetized plasma, to extend far into space. And these have a very wide footprint. So when when coronal hole high-speed streams are present, which is very common, there's a very high likelihood that the Earth in its orbit will pass through one of these areas. Conversely, coronal mass ejections are much more powerful in terms of their effect on the Earth, but their, I'll just call it beam width, just to use a term that many hams are familiar with, is relatively narrow. So the probability of the Earth orbiting through a CME is very, very much smaller than the probability of the Earth passing through a coronal hole high-speed stream. The good news is that coronal hole high-speed streams are much less severe in terms of their impact than CMEs. They don't cause extreme events like happened on May 10th and 11th, just about a month ago. And this is an image on the left, shows one of the largest coronal holes ever seen. You're looking at an image of the visible disk of the sun, and you can see that this coronal hole was so huge that it occupied about 20% of the visible surface of the sun. Not many are like this. What we worry about from a propagation disturbance point of view is primarily the part of the coronal hole that sits near the sun's equator. It's the coronal holes that are facing directly at the Earth and are near the equator that have the most significant effects. Those that appear at much higher latitudes have less effect. And the cartoon on the right side it just illustrates the open magnetic field lines that flow from coronal holes into deep space. So coronal holes occur throughout the solar cycle, but they become much more of a problem during the declining phase of the sunspot cycle. So after we get past solar maximum phase in about 2 years, we'll start to see more and more of these coronal hole high-speed stream events. But fortunately, their effects typically last for a fraction of a day, and their effects on propagation are nothing at all like what we experienced on May 10th and 11th. Their effects can be amplified by the orientation of the sun's magnetic field, and I'll discuss that in just a moment. So this cartoon illustrates some of the important aspects of the sun. It shows sunspots on the left side, coronal mass ejection. So this is literally an ejection of billions of tons of plasma from the sun, ejected at quite high speed, and some of the other aspects of the sun. So let's take a look at the rotation of our star. Remember, the sun is a gas star, so it has different rotation periods depending on latitude on the sun. The part of the sun's latitude that we most care about is the area where sunspots appear. So that really affects our propagation. And they occur at latitudes that rotate at about 27-day repetition period. So when you hear about the 27-day rotation, what that's referring to primarily is active regions that contain sunspots, solar flares, and CMEs. Conversely, coronal holes that we just spoke about, these are these open magnetic fields that cause much less severe problems with propagation. Their repetition period is typically about 25 days, so a little bit faster. The rotation period at the sun's equator is actually 24.3 days. But of course, the coronal holes don't appear exactly at the equator, so a 25-day rotation period is pretty accurate. So the sun, or the Earth, we all know about the Earth's rotational axis. That's what causes the seasons on the Earth. So the Earth is tilted 23 degrees. The Earth's magnetic field is not tilted as much. It's tilted about 11 degrees. But there's a similar situation on the sun. Its rotation axis is tilted about 7 degrees. And its magnetic field is tilted the same amount, 7 degrees. So this causes pretty strong seasonal effects as the Earth's magnetic field interacts with the magnetic field coming from the sun. And the main thing and the most easily observable aspect of this is that during the equinox periods, so that would be March, April, and late September, October, we tend to get much more severe disturbances from the sun, from CMEs, coronal holes. They tend to be much more severe. The orientation of the Earth's magnetic field with respect to the sun and of the sun's magnetic field with respect to the Earth is as bad as it can be. Conversely, and the reason why propagation tends to be so good during the month of June is the magnetic field of the sun and of the Earth is tilted in such a way that it minimizes the effect. Doesn't eliminate it totally, but we have roughly 50% less periods of severe geomagnetic disturbance during June and December than we do during the equinox periods around September, October, and March, April. So this is really kind of the Goldilocks part of the year right now, where disturbances are uncommon, but we get all night long propagation, especially on 12 meters, 15 meters, 17 and 20 meters. It's quite remarkable at this time of the year and at this part of the sunspot cycle. These images show solar flares, and on the right is what's called a prominence. It's a explosion from the sun that never escaped the sun's gravity. But just compare the size of these events to the size of the Earth for comparison. They're enormous. And about 90%, 95% of all solar flares occur when the solar flux index is 90 or greater. So they're not very common during the solar minimum phase, but they're very common right now during solar maximum. They occur just about every day. So let's go back to May 10th and 11th. We had a very severe X-class solar flare that occurred during that period. And we also had coronal mass ejections. And the effects were quite severe on the sunlit side of the sun. So during this, some of the time when the Earth was when the northern hemisphere of the Earth was pointed directly at the sun, like it was during the day on Saturday, propagation was very bad, not only from CMEs but also from solar flares that kept popping off during that period. It wasn't quite as bad at night from the solar flares because we don't see the radiation from them at night, but the effects of the CMEs were pretty bad. But after about midnight on that Saturday night, the HF band started to pretty steadily improve. So I was concerned that effect might continue for quite some time, but it actually remedied itself pretty quickly. X-class solar flares produce very strong X-ray radiation. And as I mentioned, it only affects propagation that crosses the daylit side of the Earth. Now, that doesn't mean that it won't affect our DX propagation if we're in darkness, because if we want to propagate over the sunlit part of the sun, then it may very well affect propagation paths going that way. For example, at this time of year, the polar regions of the sun are in daylight all of the time. So propagation extending almost directly north can be pretty badly affected by very strong solar flares. But don't worry too much about solar flares because unlike CMEs, propagation returns to pre-blackout conditions very quickly after the onset of these flares. The other kind of effect that generally doesn't affect us very severely, but if you look at some of the NOAA propagation or NOAA space weather reports, they refer to something called polar cap absorption. These are caused by proton radiation from very intense solar flares. And what this graphic shows, this happened to be taken during the winter when the South Pole was oriented towards the sun, more towards the sun than it normally is. And that polar cap absorption event on the South Pole was very severe, but it was very minor across the northern polar region. So these effects vary quite a bit. Fortunately, the S1 class polar cap absorption events have almost no effect on HF propagation. You can pretty much ignore them. The S2 events, and there's typically about 25 S2 class polar cap absorption events per solar cycle, they have a pretty minor effect on HF propagation. But the S3 or stronger can pretty much black out propagation over the poles, particularly whichever pole is pointed towards the sun. Now, companies that operate aircraft that fly polar routes especially pay attention to this because these proton events can really affect passengers. So there was an S2 class event during the May 10th, 11th period, and what the operators of transpolar flights did was they reduced the altitude they were flying at from their normal 35 or 38,000 foot altitude down to more like 20,000 feet to protect themselves. So the forecasting of this stuff is pretty important, especially for flights over the polar regions. And I'm not going to read all of this again. I've already mentioned all these topics, but you can look at it later if you wish. Coronal mass ejections are much more focused than solar flares. So most of them, fortunately, most CMEs miss the Earth. And those that do affect the Earth are usually near misses. But the May 10th, 11th event was very close to a direct hit, which was one of the reasons it was so severe. Fast CMEs, which is the type of CME that we had that affected us on May 10th and 11th, are the dominant cause of very strong geomagnetic storms. And that's what we had on May 10th and 11th. But we had something else that was very important in terms of affecting the strength of the storm that resulted. And it's referred to in the paragraph at the bottom of this slide. Coronal mass ejection impacts are greatly magnified when the sun's interplanetary magnetic field, so this is the extension of the sun's magnetic field out into space. When the sun's interplanetary magnetic field persists in a southward orientation, and that's exactly what it did on May 10th, which is opposite to the Earth's magnetic field. When that happens for more than a few hours, and on May 10th, it happened for most of the day, the effects of the CMEs are greatly magnified, and that's exactly what happened on that day. This cartoon kind of shows what happens in these events. Remember, the interplanetary magnetic field is just an extension of the sun's magnetic field out into space. And on May 10th, the IMF was predominantly oriented southward and for many hours. And the Earth's magnetic field is opposite. So if you remember from elementary school experiments when we might have used a couple of horseshoe magnets, and if we oriented them in the same orientation, north to north, south to south, those magnets push themselves away from each other. But on the other hand, if we oriented them the way this happened on May 10th, so they're opposite to one another, they actually attract with great force. And that's what happened for many hours on May 10th and contributed to the very strong strength of the disturbance we experienced on that weekend, especially on Saturday. And just amplifies on that. Fast CMEs, those are the CMEs strong enough to escape the gravity of the sun. They occur most frequently during the 7 most active years of the solar cycle. So they don't happen very much during solar minimum, but they happen very frequently at this part of the solar cycle, but the vast majority of them never affect the Earth. But there are big exceptions like May 10th. And all of these events happened on May 10th. So the CMEs are most likely to affect the Earth when they originate from the center of the visible disk on the sun. So within plus or minus 30 degrees latitude on the sun and roughly plus or minus 30 degrees longitude from the sun's central meridian. The central meridian is the part of the sun's solar disk that's pointed straight at us. And that's exactly what happened from the CME that affected us on May 10th. Let's just look at some of the things that are likely to affect propagation from all of these things we just talked about. Solar maximum propagation conditions began in earnest in December of 2022. So about 18 months ago. And the amount of solar activity, sunspot activity, increased dramatically over the next 4 weeks. And we were looking at how rapidly that was increasing and thinking, gee, is it possible that we could be on the precipice of another very, very strong solar cycle? Well, unfortunately, what happened is we did experience some surprisingly good propagation in January of 2023, and it was pretty good in February and March, but it continued to decline throughout the year 2023 until later in 2023 when solar activity really started to pick up and we started to experience the kind of solar maximum propagation that we've experienced for most of the last year. So what are some of the things we experience? Anybody who's on the air is experiencing this just about every day. 10 and 12 meters are dramatically improved. I'll discuss why 10 meters tends to fade away somewhat during the summer. I'll discuss that in a couple of minutes. But 12 meters is still very good and stays open well into the evening hours. But unfortunately, it's going to fade away as we get more into the July-August period. On the other hand, 17 and 15 meters are likely to persist, even during the summer, are likely to persist with pretty good propagation, even well into the night, through July and August this summer and probably next summer as well. So what we'll tend to do as we get deeper into the summer is our activity will tend to focus more on 15 and 17 meters and less on 10 and 12 meters. The other thing that a lot of hams don't realize is that 20 meters during the summer especially becomes mostly a nighttime band, and 30 and 40 meters stay open throughout the night during the entire solar maximum period. 30 and 40 meters are open almost all night long. During solar minimum, what we experienced 3 or 4 years ago is that 30 meters especially went completely dead during the night. And it's quite the opposite right now. It's just an incredible DX band during the night, as is 40 meters. Unfortunately, the nights are much shorter at this time of year, so we don't get the kind of worldwide nighttime propagation in the summer that we experience in the winter, because the nighttime, the periods of darkness are much shorter in July than they are in December. But nonetheless, 30 and 40 and 20 are wonderful nighttime bands at this part of the sunspot cycle, and that'll continue through the summer. For anybody that does field day, for example, 20 meters is a great nighttime band. It can be a bit of a struggle during the day, especially at this part of the sunspot cycle. If you recall, early in my presentation, I showed that Marshall Space Flight Center forecast of geomagnetic activity, showing how that's forecast and very highly likely to become more common and more severe over the next 3 years. So we'll be in this situation over the next few years of gradually declining sunspot activity, but gradually increasing likelihood of disturbances. That's just a normal part of the sunspot cycle. After about 2026, we'll start the gradual but inevitable decline to solar minimum, but it takes quite some time. So we're going to have still some pretty remarkable propagation even after 2026. So the higher bands, especially 12 and 10 meters, they're at their best from about the middle of September through late May. So anybody that's been active on 10 meters over the last month has surely noticed that worldwide propagation on 10 meters is much less common now than it was up through May. And that's going to continue to get worse during the course of the summer. But the good news is that although F2 propagation will be much worse during the summer on 10 meters, sporadic E propagation, which is not a topic of this presentation, but sporadic E propagation becomes much more common in the summer. So we get some pretty amazing openings on 10 meters during the summer, but it's a fundamentally different type of propagation. That especially occurs from right about now in June through the middle to the late part of July. Sporadic E pretty much disappears by the time we get into August. During solar maximum, 20 meters is a very reliable daytime and nighttime band throughout the year, with one very important exception, and that is during midday hours from June to September. And what happens on 20 meters during the day, and it's very, very apparent if you try to operate on 20 meters at this time of year during the day, and that is that the E region of the ionosphere, maximum usable frequency, extends into the 20-meter band during the middle of the day. And what happens is that propagation that we would like to extend from our antennas up into the F2 region so we can work worldwide DX. During the middle of the day, instead of it propagating to the F2 region, our signals hit the E region during the middle of the day and come back to the Earth. So during the middle of the day on 20 meters, for example, field day coming up soon, what we typically work during the middle of the day are stations within about 1,000 miles or 1,200 miles away. And for DXers, that's a nuisance. For field day people, that's a good thing. But then later in the day, the E region settles down, and during the night, 20 meters becomes a fantastic worldwide band, really throughout the year. And as I mentioned earlier, 30 and 40 meters are great nighttime bands throughout the year, including the summer. 80 meters degrades pretty badly, especially in the summer. not only during solar maximum, but throughout the solar cycle. But it provides good nighttime worldwide propagation from October through April. Not as good as some of the higher bands, but there can be some remarkably good propagation on 80 meters during the night from October through April. And 160 meters, well, 160 meters is a very challenging DX band, and especially during solar maximum. But you can still work stations very far away, but you need to be a very patient, dedicated DXer in order to do that. So I'm not going to read all of this information about 10 and 12 meters. It's a fantastic, these are both fantastic DXing bands during solar maximum, especially from mid-September through late May. But 12 meters is still remarkably good right now. I was on the band the last couple of days, and it's still quite good, but it's inevitably going to fade away as the middle of the summer approaches. But that just means that we shift our activity from 10 and 12 meters down to 15 and 17 meters and 20 meters at night, and the fun goes on during solar maximum. And I think I've said all this stuff about 15 and 17. These are both great bands, and they've really become bands that are open all night long during this part of the sunspot cycle. It's really quite amazing to flip on the radio at 2 a.m. and hear signals from all over the world coming in on 15 and 17 meters at 2 o'clock in the morning. But that's the joy of solar maximum. The propagation on 20 meters is remarkably good during the night, especially in the winter. On 20 meters, we don't so much get all night propagation on 20 meters, but we tend to have a peak in the MUF that occurs right around European sunrise. So from about 0700 to 0900 Zulu. And for contesters especially, this is really important because most contesters miss this opening. They're suffering with 40 meters, and 20 meters is red hot during those hours. And there aren't that many US stations on the band. They didn't know about the opening and they missed it. Similarly, propagation to Japan and East Asia is strongest shortly after sunrise in that part of the world. So that's about 2130 Zulu. But during this part of the sunspot cycle, sometimes that propagation can go on all night long, rather than just for a few hours like during solar minimum. But the problem in the summer on 20 meters, as I mentioned, is this E region MUF that blankets propagation that would otherwise get to the F2 region. And that's very, very apparent on 20 meters in the middle of the day at this time of year. 40 and 30 meters are wonderful nighttime bands. And most hams, when they think about solar maximum, forget that both 40 and 30 meters are greatly improved at night during solar maximum, especially 30 meters. It stays open all night long. It's a wonderful DX band, and much more so than at solar minimum when that band is pretty much dead during the night. 80-meter propagation. Unfortunately, at this part of the sunspot cycle, the propagation is pretty poor right around our sunset period. It picks up a few hours later. But usually only during the period from October through May. So unlike solar minimum, during solar minimum, we can have 80-meter propagation that's really good that extends throughout much of the night. But during solar maximum, those openings are shorter. And the 160-meter band, well, for the most part, that band gets relegated to 160-meter specialists. But if you've got a good antenna and an extraordinary amount of patience, you can work the world on 160, but you need to really work at it. So I'm going to close out the presentation. Ionospheric propagation is unbelievably complex. And the propagation forecasting programs that attempt to deal with that are nowhere near as sophisticated as what is needed to do accurate day-to-day forecasting. I like to think about ionospheric conditions more in terms of the complexity of weather and all of the tremendous number of variables that we've talked about, only some of those variables. Just for example, one thing I did not mention in this presentation, and I'm not going to go into any detail, is that the atmosphere, the ionosphere sits on top of the atmosphere. The ionosphere is also greatly affected by winds and tides at the high altitudes of the atmosphere, just below the ionosphere. So that's another aspect of propagation that propagation forecasting programs do not attempt to deal with, but they affect propagation in a very important way. Well, we live in the 21st century, and we have the good fortune of having access to tools that tell us in great detail exactly what's going on with propagation. So we don't really need frustratingly inaccurate forecasts. They should get better over the years than they are right now. But from day to day to day, they're not very good at all. But this nowcasting data that we have access to on the web shows us exactly what's happening now. These tools are very, very easy to use, and you really can't break the website. So I would just encourage you to go to these websites and experiment with it. This is the website of the Reverse Beacon Network, and you can use the fields that you see at the bottom of the screen. Spotter is the station where the receiver is located, and spotted is the location of the transmitted signals that those receivers receive. So if you look at this map, the blue dots on the map were signals transmitted from Europe, and the red dots are the receivers on the Reverse Beacon Network that received those signals. And the green lines were added by the software that just shows the propagation path. Using this tool, you can explore a wide variety of current activity on individual bands, on many bands, many different areas of the world, or very focused areas of the world. For example, you can select just one CQ zone, or one DXCC country, or one continent like North America, both for the location of the receiver, where the red dots are, or the transmitter for the blue dots. Very easy tool to use and very powerful. It only shows current propagation. The map that's shown on the screen right now was taken at midnight in December, and it shows 80-meter propagation from Europe to North America. The other websites that I like to use are PSK Reporter, and this is a particularly effective website because there are so many stations reporting back to the PSK Reporter server. And this shows 20 meters early in the evening, and you can see all the propagation from Europe and South America, and some from the Far East getting into the US. Another tool that's very easy to use. I'd encourage you to learn how to use it. This is by far preferred to using forecasting data. The other tool, and I don't have a graphic for that, but it looks very similar to this, is DX Maps. And that's another one a lot of people like to use. And it's the same thing. It's nowcasting, showing current propagation. So the last thing I want to leave you with is for the last 3 years, I've been publishing a daily propagation forecast in the daily DX. And just before the ARRL CW DX contest, on the Thursday before the contest, I published this forecast for the contest. And it unabashedly forecast the best ARRL CW DX contest propagation in more than 20 years is likely this weekend. So that was the forecast on Thursday, with a combination of high sunspot activity, quiet geomagnetic activity, quiescent solar wind, and low polar cap absorption. Well, I got lucky, and all of those things that were in that forecast that was published on Thursday proved to be exactly true. And it was arguably the best ARRL CW DX contest propagation in the history of that contest. And anybody who wants to take a look at those daily forecasts, you can go to the Daily DX website and as shown, and you could get a couple of weeks trial subscription and see if that forecast is of any interest to you. So that's the end of my presentation. And if anyone has any questions, I'll be happy to do my best to address them.
Frank, Eric, WA1S6K, I have a question.
Hi, Eric.
Yeah,
Go ahead.
Frank, yeah, good evening. Thank you. Great presentation. I wanted to ask you a question that was a totally new concept that you mentioned earlier in a slide. It showed the solar cycle, and I believe you had a northern hemisphere propagation, and you had a southern hemisphere propagation.
Right, those are actually sunspot numbers, Eric. It's not
Okay.
propagation.
Oh,
Yeah.
sunspot numbers, so they're actually different in the south than they are in the north?
Yes,
Where they're hitting?
and take a look at this slide. During the last sunspot cycle, there was if you look at the purple line on this slide, notice how much the sunspot activity in the southern hemisphere picked up during the year 2014. It was unexpected and dramatic.
So, to the new concept I'm learning then is, so the sunspot numbers are different in the southern hemisphere than they are in the north?
Yes, and you can see that in this actual data.
Correct.
But take a look. The last sunspot cycle was quite dramatic. The light blue line is the northern sunspot number, and notice it's very similar to right now. Very similar numbers. On the other hand, the southern sunspot number dramatically increased in 2014. And that has not happened in this sunspot cycle.
Gotcha.
And I
Okay.
think it's unlikely. And for a couple of reasons. One is we're getting a little bit late in this sunspot cycle for that to happen. But the other thing is, if you compare how that light blue line and the purple line tracked in the last sunspot cycle, they were significantly out of phase by a few years throughout the whole cycle. On the other hand, if you look at the light blue line and the purple line in this cycle on the right-hand side of that chart, notice how they're tracking each other pretty closely. So they're pretty much in phase. But boy, I would love to see that purple line explode later this year or next year, like it did 10 years ago. I've got my fingers crossed.
Right. Okay. Thank you, Frank.
Okay.
Say, Frank, this is Walt, AJ6T.
Hi, Walt.
Do you have any thoughts on why the 6 meter sporadic E season this year seems to be off to such a slow start?
I certainly have thoughts, but keep in mind the operative word is sporadic. That's the operative word. And I have another presentation about the same length as this one that deals with sporadic E. I don't have time to go into all that detail, obviously, tonight. But if you guys would like me to do a presentation on sporadic E at a later date, I'll be happy to do it. But sporadic E, I'll just mention a couple of the key points. Number one, it has nothing to do with everything I've spoken about over the last hour. Everything you heard me talk about over the last hour, forget it, as if you've never heard it. It doesn't relate to sporadic E. So for everything I've talked over the last hour, almost all the effects come from the sun. On the other hand, for sporadic E, the ionization mechanism deals with the influx of probably what is most easily described as space dust. Some people refer to it as micrometeorites, but it really is dust. And it's mostly metallic. And that's what causes the ionization that we refer to as sporadic E. But that's not enough. If it were only that, it wouldn't reach enough density for the propagation to extend all the way up into the 6-meter band. And this is where things get complicated, because that influx of space dust is about the same every day during the summer. It does have a seasonal variability, but if you look from day to day to day during June and July, it's pretty much the same every day. But on the other hand, in order for the ionization of that space dust to become dense enough to cause 6-meter propagation, the ions and the electrons associated with that have to become compressed into very thin areas, typically only about 1 kilometer or 2 kilometers deep. And in order for that to happen, meteorological events have to happen. Meteorological winds at high altitude. And that meteorology, just like weather on Earth, is highly variable. And it has not only variability day to day, but it also, different years seem to have different kinds of meteorological characteristics at these high altitudes. So unfortunately, so far this year, so we're already about 25% of the way through the sporadic E season. Sporadic E season runs from roughly the 1st of June until the middle or maybe a little bit late in July. Well, we're already 25% of the way through that season. And it's been pretty disappointing. For the most part, what we've had is one hop sporadic E, propagation that carries about 1,200 miles, and very, very little of the long distance sporadic E that gives us an opportunity to work into Europe and Japan, or even into the Indian Ocean. This year has been terrible. And I would attribute that to meteorological considerations, where the high altitude winds that are needed to compress this ionized space dust is just not occurring frequently enough or in the right places for us to enjoy the kind of incredible sporadic E propagation we had 2, 3, 4, 5 years ago. It was really amazing. There's another aspect that may have an effect, but this is unproven. So I'll just mention this in passing, because there's significant disagreement among scientists. But Earth's magnetic field, as it passes through the E region, also has a very significant effect on the formation of these sporadic E clouds. But how severe it is still subject to some debate. So it's kind of postulated that this is the case. It certainly appears to be. Many of us who operate 6 meters have a pretty strong opinion that 6 meters long distance sporadic E, not the single hop stuff, but the long distance stuff to Europe and Asia seems to be much more prevalent during the solar minimum years than it is during the solar maximum years. And what's the difference? In the E region, it's geomagnetism. In other words, the K index or the A index. But we'll see. Hopefully, some of the scientists that do this research will ultimately agree that there is or is not an effect that affects sporadic E. So that was probably a more complicated answer than you were hoping for. I'll just close out by saying it's the magic band. And sometimes the magic works to our benefit and sometimes not.
Well, thank you, Frank. That's exactly what I was looking for.
Okay, great. Well, any other questions?
Yeah, Frank, Ed, K3DNE, I have a question.
Hi, Ed.
Hey, how are you?
You could probably yell at me and I'd hear you.
Not anymore. I've moved.
That's right. You've moved out of the area. That's
Yeah,
right.
I'm in South Carolina. So it's ironic that that question was just asked. I'm looking at DX map and PSK reporter right now. I'm not in the shack, but it shows an opening between the Midwest and JA as we speak on 6 meters.
Very good. Yep.
It looks very isolated on our end. My question, though, is something that you didn't touch on, but it's a conversation that keeps coming up with some of the people that I speak with, and that's the mechanism of HF backscatter, especially during the solar cycle peaks. You hear all sorts of rumors and propaganda, and you read things about reflections off of ocean waves and off of mountains, but I've read a recent article that it's more ionospherically associated, and I was wondering if you have an opinion on that.
My opinion is that the strongest backscatter does in fact come from disturbed sea conditions where the waves are very large. So they're in the order of wavelengths at the HF bands. And those reflections are very intense, as is reflections from mountains, but they're not as strong. But certainly the scattering mechanisms in the ionosphere have a role, but those scattering mechanisms in the ionosphere tend to be rather inefficient. So they normally wouldn't be associated with really strong backscatter. But all of them happen. So that you get weaker scattering from some abnormalities in the ionosphere. The ionosphere is not smooth by any means, but you get very strong reflections from very disturbed sea conditions and from mountain ranges. Let me mention one other thing, Ed, about this propagation to Japan that you just noticed. And that's just a great advertising for why nowcasting is so important. It's really great. You can detect these openings without having to glue yourself to your computer screen. From Maryland, where I live, the propagation path to Japan goes up over in Michigan. And the best indicator I have for the possibility of very long distance propagation from Maryland to Japan on 6 meters is when we have strong sporadic E from Maryland into the upper part of Michigan. And when that happens, all fireworks can break out. But it's sporadic E, and it's very sporadic. So, but on those days when it happens, boy, 6 meters propagation to Japan is just wild. I'm not expecting that, though. We didn't have very much of it last year, and we've had none of it so far this year.
Frank, this is Zori, KB3VQC.
Hello, Zori.
Hello. I wanted to compliment you and say another beautiful presentation. Thank you for sharing with us.
Yeah, thank you, Zori. Well, what I always try to do is to make this relevant to hams. You can research this in professional publications endlessly, but then it's hard to relate it to our experience and interests as hams. So what I try to do in my presentations always is to take it out of the theoretical realm to the extent you can and apply it to our everyday experiences on the air. So are there
Any other questions for Frank?
Okay, so I guess there are no more. If you guys would like me to do a sporadic E presentation that's similar to this, I'll be happy to do it on a future date. I suppose we should have done it on this date since this is the magic time for long distance sporadic E during the course of the year. It's early June to mid to late July is the magic time on the magic band. But I'll be happy to do that presentation in the future.
Well, that would be great. This was a fantastic presentation, regardless of the season. And as you just said, taking all this data from NOAA and other places and translating it into things that is not only understandable, but also actionable for DXers like us is really great. So thanks an awful lot. Bob, any final comments?
Oh, just thanks for a great presentation. Frank, I really appreciate the very up to the minute data you presented us, and I enjoyed your insightful comments about the data on the Southern Hemisphere. So thanks so much for that. Great presentation. Thanks a lot.
Okay, and if anyone has any questions at all, feel free to drop me an email at the email address on the first slide, and I'll be happy to respond to the best of my ability.